Next we see our third method, which is called as heuristic based method. So in this method, we actually assign priorities to certain conditions based on our state transition graph. So let's say if you have two states, alpha and beta, and we have a condition, they go to the same state for the same input, then it gets the highest priority. So which means they are to be placed next to each other in your state map. So if again state alpha and beta are sharing a common ancestor, then again that gets medium priority, and then the lower priority is for two states alpha and beta as far as they have the same inputs and outputs, and they're going to two different states or going to anywhere, then they get the lowest priority. So you need to memorize these priorities, and as you can see, here is an example where we have states S0, S1, S3 and S4, and so these are actually some reduced state transition graph. That's why we don't have S2. S2 has been eliminated by state minimization. So here we see that S3 and S4, they actually go to S0, and that happens when you have a condition which is 0 0 and 0 1. So you have one such condition that exists. You don't have another one for say 1 0, and here again is 1 0. So we don't have that particular condition in here. So therefore that gets the highest priority, S3 and S4. That becomes alpha and beta. So now again, as you can see, S1 is the common predecessor for S3 and S4, and as you can see, irrespective of what they have, so they'll get medium priority. And then similarly, all other instances like S0 and S0 with S1, which has 0 0, and S0 with S3 has 0 0, and then again we can also have so therefore we have S0 and S1 and S0 and S3, and similarly so we have other instances like S0 and S1 for 0 0 case. Then we have S0 and S3 for 0 0 case. We have S3 and S4 for 1 0 case, and so on. So you have different combinations. So these pairs, so when we are actually writing them like this, so we actually have to see that S1 should be adjacent to S1, S0 is adjacent to S1, S0 is adjacent to S3, S1 is adjacent to S3, and so on. Similarly here we have S0 adjacent to S1, S0 adjacent to S3, S0 adjacent to S4, S1 adjacent to S3, S1 adjacent to S4, and S3 adjacent to S4. So all these will have lower priority. So when we actually make our diagram, which is the state mapping diagram, so we need to make sure that we have so we have only 4, so we only have this, and then we have 0 1, 0 1, and these are our variables here. Let's say state variables A and B. So when we actually assign them, we can actually say so we have S3 is adjacent to S4, and then we can see in this case we have more things to do with S0. So therefore we put S0 adjacent to S3, and then S1 is also adjacent to S4, And so this is the best possible assignment in this case. Here is the next other problem. So here you can see we have over here 0 0 and 0 0 from S3 S4 going to S7, so which satisfies that. So therefore we have that. And similarly from S7 S10 to S0 we have two conditions. One is for 0 0 and 0 1, and the other one is 1 0 and 1 0. Therefore it will be twice of that. And then similarly you can have medium priorities for S1 S3, 2 times S3 S4, 1 time S7 S10, and then lower priority for all combinations of these. So in general we would need to first take care of this, so therefore you can have S7 needs to be close to S10, and then go for S3 close to S4, and the lower priorities can then follow. So there are two problems that I'm going to leave the students to actually solve them. So this is basically a validity checker for the BCD digits. So as you have an input which is X, and as you have a system, as the inputs come one after another, so we would check for a pattern for a valid BCD number. So if that is a valid BCD number, so we actually have Z is equal to 1. So for example, an input of 1001, when it actually comes, you will have Z is equal to 1. And then if you have, for example, another 0, again you have an output is equal to 1, and so on and so forth. So if you have some instances where you have say 1101, then that is not a valid BCD number. A BCD number can only go from a value of 0 to 9, so that is not a valid BCD number, and you'll get a 0 as an output. So here is the state table in its complete form. So the students are expected to reduce this table to a state minimization. So here you can see we can quickly do the state minimization as shown here, and then apply a bit change or a heuristic method in order to assign codes to those states. And here is another problem that will be solved in a different video. Here we have the state diagram that is actually given in millis mode, and we are going to use 1-hot encoding. So in 1-hot encoding, let's assume that you have, these are your values. So therefore we will actually inspect this table and actually derive the expressions for your flip-flop inputs directly. So in completion, we have seen how to perform state assignments to sequential circuits using the bit change method, 1-hot encoding, and heuristic method that was shown at the end. Thank you.